Hi, I'm Antonio Sala, and in this video we will discuss the relationship between ellipsoid and the singular value decomposition of a matrix. In particular, we saw in earlier videos that this was the representation of an ellipsoid with P being a positive definite matrix. We could also have an inverted form representation with Q being positive definite, equivalent, of course, with the non-inverted one if both P and Q were invertible, non-singular. Degenerate cases would require extra thinking. But we also saw a third representation of an ellipsoid as a transformation of a sphere via an arbitrary matrix L, which needed not being positive definite. Just deforming a sphere gets an ellipsoid. What we will discuss now is the relationship of the ellipsoid shape with the singular values of L, when we decomposed L as USV transposed, being U and V orthogonal matrices and S a diagonal one, with the so-called singular values in the diagonal. If L is symmetric, then U and V coincide, and it will be the diagonalization of a symmetric matrix. And if L is not symmetric, then we get U and V different, and it's called singular value decomposition. So good. In order to understand what we are doing, let us first see a Matlab example of a transformation L and its meaning before computing the singular value decomposition. In here I have some angle which will cover the whole circumference from 0 to 360 degrees in steps of 6 degrees for my plots. These are the positions of 0, 90, 180 and 270 degrees. I transform to radians, and this line computes the points of a circumference of radius 1. Then, if I craft this L matrix, it's just invented, nothing special, then the points of the ellipse are L multiplying the points of the circumference. Well, that's it. It's a one-liner in Matlab, mapping a circumference to ellipse. So now let's plot it. This is just cosmetic, plotting the circumference, the ellipse, and the 4 points in the coordinate axis and its image. And this line is the one that represents the ellipsoid via a quadratic form to check that it's indeed the same as via a linear transformation of the sphere. So inverse of L transposed is what I am using here. So this is the final figure. We have a blue circle that maps into the red dots in the ellipse, which of course coincide with the quadratic equation given by inverse of L transposed, and the points 1, 0, 0, 1, etc. map to the big dots in black, green, red and brown colors. But as we see, this kind of representation forgets something. Forgets that, well, okay, the most interesting point will be this one and perhaps this one, depicting the major axis and the minor axis. So, which points in the sphere render this axis? Well, okay, sort of a couple of blue points later on, so sort of this one will map to that one, and again a couple of points later this one would map to that. But is there any formal way of computing the blue points in the unit sphere and the red points in the resulting ellipse? Yes, it is, and it's called singular value decomposition. So imagine that we decomposed L like this. Then of course this ellipsoid and this ellipsoid are the same. We just saw it in Matlab. But okay, this is L transposed. and doing operations. As V is an orthogonal matrix, V transpose V is identity, so we can delete what it's inside and end up with this. And in fact, carrying out operations as the inverse of U is also the transpose, then the ellipsoid we are obtaining can be shown to have that equation, which means that as S transposed will be a diagonal matrix, sort of Q after a rotation by U, well, this means that the rotation by U will align me this ellipsoid. And if I call this X tilde, then I will have an axis-aligned ellipsoid, and the semi-axis length will be proportional to the square root of this matrix, but okay, this is a diagonal matrix with the singular values squared, so we can conclude that U are the directions of the principal semi-axis, and the diagonal of S, the singular values, are the lengths of those semi-axes. And this is the main conclusion, and also the fact that if I choose the points in the sphere being the rows of V, then if I call that UI, then L times the first column of V, this thing will be 1, 0, 0, 0. If I use the second column, will be 0, 1, 0, 0. And if I use the ith column, then I will have the canonical column vector with the 1 at the ith position and 0 elsewhere. And then I will get, carrying out operations, the ith column of U times the singular value at position I. So this UI will be the point that maps to the principal semi-axis, the points here that we were looking for. If we plot that idea in Matlab, this means that if I carry out the singular value decomposition and I get two principal directions, so this highlighted line will plot the point in the unit sphere, columns of V, and this U times S line will plot the image of that point on the ellipse. So, apart from signs, we have formally obtained what we intuitively were asking for in the previous Matlab plot. We have proven that this point maps to this point maps to this point. Each of these two directions are columns of V in the SVD, and these thick red arrows, coincident with the major and minor axes, have the direction of the columns of U times the associated singular value. So the interpretation of that is that V are the input directions associated to the minimum gain, minimum half axis, and maximum gain, maximum half axis. And the columns of U are the output directions, telling me the directions of those half axes, and S, the singular values, tell me the length of that half axis. So we end the video here, summarizing. In this video, we have discussed the relationship of the singular value decomposition of the matrix L, arbitrary, not necessarily symmetric, with the shape of the ellipse that is generated when the points in a sphere are multiplied by that matrix L. We end the video here. Thanks for watching.